Swayam Prabha. Digital India. Educated India.
We looked at half controlled and fully controlled with R and RL load. I'll recapture that a little bit so that we will have continuity. So we started off with controlled rectifier. So what we said was, instead of diodes, we will use SCRs. Right? And diode will conduct whenever it is forward biased. There is no control over its conduction duration. So I would say that diode basically are uncontrolled devices, whereas SCR you would be able to decide or determine the instant at which conduction starts. So we would be able to delay the conduction. So because of which the voltage will get varied. So we are essentially intending to delay the conduction. So output voltage can be controlled. Output voltage, what I mean is DC voltage, can be controlled. So in whichever application we require different values of voltages as per the requirement, then controlled rectifiers could be used. We actually showed first half wave controlled rectifier. This is what we analyzed yesterday. Just quickly recapturing. So we are going to have a thyristor here. This is the power supply and this is the load. Right? So we are supposed to give the gate pulse. Here is the gate pulse that we need to give. Right? So if we are looking at a resistance load, just a pure resistance load, if this is what is my sinusoid, when it was a diode, we were talking about the entire positive half conducting from here to here. Whereas if I am going to have a thyristor, I am going to turn on this SCR. So this is the gate pulse that I am giving at an angle alpha. This is omega t. So at an angle alpha, I am essentially looking at this device being fired. So I am going to have this as the voltage, provided it is a resistive load. So I would say this is R load output. If I am talking about resistance load, the output voltage will be like this. I am sure you can derive the expression for this. It will essentially become Vm sin omega t from alpha to pi. That's it, right? So I am going to have alpha to pi Vm sin omega t d omega t 1 by 2 pi. This will be the output voltage. Output VDC average. This is the average DC output. Right? So if I write the expression for this, it will become Vm by 2 pi, of course. And I will have cos alpha minus cos pi. So I'm going to have 1 plus cos pi. Right? Cos alpha. 1 plus cos alpha. So I'm going to have this as the output voltage. Whereas if I had diode, I would have gotten this integration from 0 to pi, because of which we got Vm by pi. Right? So Vm by pi is definitely higher than Vm by 2 pi multiplied by 1 plus cos alpha, provided alpha is greater than 0. So I'm going to have a variable voltage. This is what I was trying to get at, because repeatedly there were questions as to why we are having a thyristor. Why should we have a thyristor at all? Or why should we delay the firing? We are delaying the firing essentially to get a variation in the output voltage, right? So I would say output DC voltage for a diode half wave rectifier is Vm by pi. So compare these two to find out how the controllability is in one case versus other. Whenever I am going to have an SCR, I will have reduced voltages provided I am delaying the firing. I am talking both the cases about same R load. Whereas with RL load, it's not going to be so simple, because the current can start from here and then it can extend for longer, because of which even this portion would appear, right? So this will appear only for RL load, not for R load, right? And I should know at what point the conduction is being completed, which is beta. So I have to integrate between alpha and beta has to be solved for by first of all solving for current. After solving for current, the initial condition will be Ia of alpha equal to 0, I of alpha equal to 0, and again I have to put I of beta equal to 0 to solve for beta in that expression. That's how we solve for beta. So this is the difference between what we had as uncontrolled rectifier and what we have as controlled rectifier. Just to recall what we did as the second portion of this rectifier circuit, where we had 4 thyristors and we had an RL load, and we looked at 2 cases, one of continuous conduction, the current is continuous, and another case of discontinuous conduction. Both we had taken a look. With the source that is being connected is a single phase AC source, and most of the times the sources that we consider are generally of 50 or 60 hertz, because these are all power frequency rectifiers, power frequency AC to DC converters, right? So we will normally assume that the frequency of operation is very slow. So the devices will have sufficient time to turn on and turn off. That's the reason why we use thyristors, which are pretty much slow compared to IGBTs or MOSFETs and so on. We are not going to use any of them, right? So in this case, we numbered these as 1 and 4, and we call this as T2 and T3, and we call this point as A and this point as B, and we said this is an RL load. Just to reiterate, we essentially drew different waveforms, that is the supply voltage, load voltage, supply side current and load side current. These are the things we drew. So if I am looking at the supply voltage somewhat like, like this, and if I am going to assume that I am firing 1 and 4 at a firing angle of alpha, then I have to fire the other 2 at pi plus alpha so that it will be symmetrical. I will have symmetrical way of firing this. So now if I assume it is continuous conduction, the current can never be 0. It has to be at least some value. So if I say that it is starting from some value, so maybe it is starting off with some value. So from here, it is going to start increasing like this. It is increasing, and at some point it will start decreasing. Let's write the equation again. Ri plus L di by dt equal to Vm sine omega t if I am having T1 and T4 conducting. If these two are conducting, I am going to have Vm sine omega t directly applied across the load. Whereas I am going to have, this will be equal to minus Vm sine omega t if T2 and T3 are conducting. Because just the opposite polarity is connected right across the load. That's the reason. Right? Now, if I'm going to have L di by dt equal to Vm sin omega t minus Ri, we already said when these two are equal to each other, the current is going to reach its maximum value or minimum value, because of which, let us say at this point it reaches the maximum, and from here it is going to start dropping down. Right? Correspondingly, I can draw probably the voltage waveform, which is I times R, somewhat like this. So at this point it reaches the peak, and at this point it starts declining. So this is I times R, whereas this is going to be I. Right? Now I am going to have, at this point I am firing 2 and 3. At this point I am firing 2 and 3. So until now, Vm sin omega t was directly connected as it is. So I'm going to have this entire voltage coming up as the load voltage on the whole. That is how it is going to come up. And then I'm going to have this portion again coming up. This portion is going to come up. Get my point? So I'm going to have this shaded portion as the DC voltage or the load voltage that comes up when I am having continuous conduction. So the current, you can see, is oscillating between some peak value and some minimum value. So it is going to repeat itself again. I have to have this repeating again. So this is going to be the current waveform. So if I try to look at what is the current waveform that I see from here, which is the supply side current. Whenever 1 and 4 are conducting, I'm going to have a positive current that is flowing in this direction. I say that this direction is the positive flow of current. Whenever 2 and 3 are conducting, because it is conducting during the negative half cycle, this will be plus and this will be minus. So because of which the current is going to go in the opposite direction. So I should say the conduction duration, I can write it somewhat like this. From this point to this point, 1 and 4 are conducting. From this point until again, if I call this as 2 pi plus alpha, I am going to have 2 and 3 conducting. Right? So during this portion, if I try to draw the current, it might just increase like this and then decrease like this. This is the current corresponding to 1 and 4, and this is the current corresponding to 2 and 3, and this happens to be the supply current. This is how the current is going to be. So abrupt rise and abrupt fall is going to take place as far as the supply side currents are concerned. But they are exactly shifted. If you try to look at the supply side current, it is exactly shifted from the voltage zero crossing by an angle alpha, whichever is the delay angle. That is how it is going to be shifted. So I will have the phase shift between the voltage and current to be actually alpha, because voltage had the zero crossing here, whereas current is having the zero crossing here. Right? So I will have, the shift that is coming up between positive going zero crossing of the voltage and positive going zero crossing of the current, and negative going zero crossing of the voltage and negative going zero crossing of the current. The shift is exactly the same because I have done symmetrical firing. Yes. We are not starting with transient. I told you that if we start from transient, it will start from zero. Inductance will slowly accumulate energy. We are talking about the waveforms in steady state. In steady state, and if I am considering continuous conduction. If it is discontinuous conduction, it will start from zero, what we discussed yesterday. I don't know whether you were there yesterday. Yeah, you asked the question also. Yes. So if you look at the discontinuous conduction, it would have started from 0. If it is continuous conduction, it will not start from 0, especially in steady state. When you are talking about transient, yes, it will start from 0. But when you are talking about steady state, all the minimum values will be at the same level. Similarly, all the maximum values will be at the same level. When that happens, that is when you call it as steady state. Yeah. No, not at all. Even in the transient, you have to start with thyristor only, because you are not changing the circuit. You are starting off with dead position of the circuit. It's dead, completely dead. You are applying a voltage. The current will start from 0. At alpha, whichever alpha it is, at that alpha, the current will start slowly increasing. It is RL circuit, so the current cannot jump. So it will slowly increase. As it builds up, you are going to see that inductance stores energy. So at whatever point Vm sin omega t becomes equal to Ri, the current has reached its maximum, there is no more energy to supply to the inductance, then the current will start declining, because of which inductance will be able to pitch in. So it pitches in until the next pair of devices are fired. The moment the next pair of devices are fired, if the current has not still touched down 0, then it is already having a head start. You get my point? So like that, it builds up energy. That's what happens. Yes, absolutely. We are talking about at a given alpha, at a particular supply voltage with a given circuit, how it slowly attains steady state, and in steady state how the waveforms look. This is what we are talking about. Right? Now, if I have an RLE load, which is like a DC motor drive, for example, which is already running, so it will have a back EMF, right? And if it has a back EMF, you are going to have definitely that back EMF opposing the current. Back EMF will not aid the current. If it aids the current, it will go to infinity, literally. So I will have essentially this as the circuit. I'm going to have the 4 devices here, and I'm going to have R, I'm going to have L, and then I'm going to have this. Okay, so now I have put the source such that the positive is here, which means it is definitely going to oppose the flow of current, or it is as though a battery is getting charged. The current is in this direction. So I'm going to have plus here and minus here. So it is, the battery is trying to accumulate energy. Right? That's what it is. Now if I am having this somewhat like this, then I'm going to have, let us say I'm talking about a 230 volts AC here. Maybe this is a 220 volts battery. For example, I'm just arbitrarily taking some values. 230 volts RMS, 325 will be the peak roughly. So I am essentially going to have a voltage waveform somewhat like this. This is 325. And what I am having here is about 220, so probably this is going to be my DC voltage. This is E, right? So, if I try to fire, for example, at this point, right? If by chance if it happens to be continuous conduction, then yesterday Apur Dhankar was asking repeatedly that why should you not consider the inductance voltage at all while you are looking at whether it is trying to forward bias, the supply voltage will forward bias the devices or not. But the load inductance is completely isolated. If I am trying to look at the whole thing as though, let's say I am trying to fire 1 and 4, and these two are, if they are already conducting, if they are already carrying a current, continuous current, In that case, I can consider them as short circuits, right? And I'm considering positive half cycle, which means plus here and minus here. So I would say plus is connected here clearly, and this is minus, and through this device which is short circuited, this is going to be connected to minus. So this is plus and this is minus. So obviously device number 1 is forward biased, irrespective of whatever is the voltage that is there in the inductance or anything. It doesn't care. Same way, I can say, if I consider device number 4, this is minus, because this minus is directly connected here. And this is plus, and this is a short circuit, so this will be automatically plus. So no matter what, this device is forward biased, irrespective of whatever happens here. From supply voltage itself, I can say this particular device is forward biased, no matter what. So, if I talk about continuous conduction even in this case, and even if my DC voltage is higher than whatever is the supply voltage at the instant of firing, it doesn't matter, the devices will get fired. No matter what, the devices will get fired. On the other hand, if I am not having the conduction, let's say it is not continuous conduction. If it is not continuous conduction, no current is flowing. If no current is flowing, this is an open circuit, this is also an open circuit. You get my point? It has to be open circuit. If it is open circuit, I have the supply voltage connected here, which is positive, but I have this plus also coming into picture here. This plus will come here because it is open circuit voltage. I have to look at open circuit voltage. When there is no current, essentially whatever is the voltage here, there is no drop, nothing here. So this voltage will appear right there. So if that voltage appears here, I have to have a tug of war between these two, whether this is dominating or that is dominating. If I'm going to have the voltage that is here, that is dominating over this positive, then it is reverse biased. On the other hand, if this is going to be smaller, I will have this forward biased. The same thing holds good for the other device as well. So there are two cases we have to consider. If I am having already continuous current, then I don't have to bother about what is happening in the RLE. I can directly say if it is positive half cycle, I will be able to fire 1 and 4. If it is negative half cycle, I will be able to fire 2 and 3. Whereas, if I am not having continuous current, in fact the current has to start from 0. At the instant of firing, I have to compare basically what is the voltage here and what is the voltage coming up from the supply. And I have to compare the two, and if the supply voltage is dominating, only then it is going to get fired. That's all the more reason why we never give a single pulse normally for a thyristor. We get a train of pulses. We generally make a pulse almost for 180-degree duration, because I would know that from here to here this device can conduct, and from here to here the other device can conduct. So this is for T1, T4, this is for T2, T3. So this is from alpha to almost pi plus alpha, and this will be from pi plus alpha to 2 pi plus alpha. So if it doesn't get a chance to fire here, at least let's give it a chance to get fired whenever it is possible for it to conduct. So thyristor circuits, as a rule, are never given one single pulse of a very short duration. Never ever. Okay. So if I am going to have actually an AC supply being supplied to a thyristor circuit, I necessarily need to give a long duration pulse. But the continuous long duration pulse normally I do not give for SCR because I use a pulse transformer. Please correlate the two. I connected a pulse transformer to isolate the gate from power. All these things are in gate. All these things are in power. Right? T1 and T2, whatever I am giving is in gate. T1, T4, T2, T3, all these pulses are in gate. And gate pulses, if I try to give continuous pulse, yes, I need to give a wider pulse, I told you. But if I give the wider pulse directly, the pulse transformer will get saturated, which I am using for isolation. So I necessarily need to AND it with high frequency. That's what we did. You remember, we ANDed it with high frequency and then we made the amplification, and after the amplification in the collector we had connected a pulse transformer. That's what we had done. So please correlate these two. We are having a pulse given here. Okay. So if I am having one pulse here, it is not going to allow the SCR to fire, especially under discontinuous conduction. So I might have to give it a chance, fair chance to conduct by giving a wider pulse. But if I give a wider pulse, because that is the norm for the thyristor normally, if I give a wider pulse directly, if you may recall, we had said that the pulse has to be given basically to an amplifier. In the amplifier, I had given a pulse transformer in the primary, which is connected to the amplifier, and the secondary was directly connected through a diode to the gate and cathode. This is how I had shown, right? So this is all 15 volts or 5 volts, all the electronics, right? Microelectronics. Whereas gate and cathode clearly is connected to larger voltage, larger power levels, right? Larger voltage and larger current. So I want isolation between the two. That's the reason I am using a pulse transformer. The pulse transformer will isolate the ground of the microelectronic side from the power side. But because I'm using a transformer, I can't afford to give a pulse which is continuous like this. It will saturate. That's the reason what we had done was to use an AND gate. An AND gate we had used with, here we had given a clock kind of pulse, high frequency pulse. And here we had given this pulse. So what you will get here will be a train of pulses like this. And then it will be 0, again a train of pulses like this. So, yeah. It will not get on, absolutely. But generally what we do is, as a rule, all the single phase converter circuits will receive a pulse of 180 degrees. That is a standard design. Although it is not going to really work, you know, even if I try to fire it beyond this, it will not work. But we generally make it like a standard practice. So all the single phase SCR controlled circuits will have a pulse width of normally 180 degrees. When we come to 3-phase, we will see it will be 120 degrees. Right? As a rule, single phase circuits will have a pulse width for the thyristor phase controlled circuits. They will always have 180 degree pulse width, whereas 3-phase controlled circuits with thyristor will always have 120 degree pulse width. We'll look at it why as to, right? So, in this case, if I assume discontinuous conduction, it will start conducting only from this point. Although I had tried to give a firing pulse at alpha, but I will see the conduction starting only from this particular point. The current will start rising from here, and it might just, you know, end up coming down something like this. It's possible. Depends upon R, L and E values, especially R and L values now, because I know exactly where E stands. Right? So this is the way the current is going to be. Obviously, in the other half cycle again, I'm going to have this as the other half cycle, and I'm trying to fire it somewhere here. Sorry, I have made it a little taller. Okay? And then I'm going to have essentially the current starting only at this point, and then it is going to probably go again